All right, I think we're rolling. Let me put the links down everywhere, and then we'll get started in a little bit. Cool. If you're watching, feel free to say in the chat. I think this is going to be mostly interactive. I did plan out some things I wanted to talk about, but I've talked about this before on YouTube, and so I think this one's going to be a little more interactive. Answer some questions that I've gotten before, and so feel free to say hi in the chat. And a couple minutes. Oh no. Internet, help me out here. Ah. Well, it's should work. We're gonna shoot for it because it looks like YouTube is doing okay. Cool. So before I dive into sort of mostly what's going to be live coding and just looking around kind of how everything works, I wanted to highlight a couple things. So I wanted to highlight, first of all, I've done a couple of blog posts recently about the topic of programming languages and interpreters. There's two that I think are particularly interesting, so I'll put them out. The first one is I've written about the idea of like building your own programming language, building your own interpreter. This one's pretty lengthy. I think it's like a 15-20 minute read, depending on how quickly you read. But it goes into it goes into all the details of sort of why you should build your own programming language, sort of how I personally approached it / approach it if I were to do it again, as well as sort of all the considerations that you do, kind of all the places that I look for inspiration. In particular, I have bits down here about sort of all the blog posts and books that I found were useful, a lot of which I used to build mine or at least get inspiration from it if it was too complicated to implement myself to read. So I think this is just a really good place if you want to start looking for resources to. It's mostly a resource bank to build your own programming language. I also wrote, if you're a little more advanced or want to get your hands a little bit more dirty, I wrote about some interesting things about the Lua C interpreter, which is a bytecode virtual machine, if you know what that means. There's some interesting design decisions that they made in designing their interpreter that I think are interesting if you want to get into that. And so if you're interested in these topics, I think those are pretty interesting, like two of the most interesting things that I've written about programming languages, and so those would be pretty cool places to start. So with that, I think how the stream is going to work is we have about 40 minutes left in the hour. I think that's going to be just fine. I think I'm going to split it up into sort of three sections. I'm going to have a bit. I'm going to have a bit about sort of how Ink works. I'm going to talk about Ink, which is a programming language I made. You can find Ink if you go to linux.zone/Ink. Ink as a programming language works, just so we can just talk about it in the context of interpreter. This is the programming language. And then for the next section, I'm going to talk about how the interpreter works. I'm going to go through and kind of show you the steps that the interpreter takes to actually run and evaluate code. And then lastly, I want to talk about a lot of improvements that I could have made, but I didn't, and how a more sort of production-ready interpreter would be different from sort of like the really basic toy version that I've made over here. I do have a stream that I did a long time ago that sort of covers these things, but I'm going to try to do a better job this time, so this can be sort of the one for permanent record. So with that, let's talk about Ink. So Ink is a sort of a scripting language, is probably what I would call it. It's inspired a lot by JavaScript, but it's a lot simpler. So you start it with Ink, and you can do like additions, it can do number operation, things like that. It can have basic strings like hello world. It can work with lists, so 1, 2, 3, 4, 5. Internally, the way that JavaScript is also the way that Ink is, in that lists are represented as objects where the keys are indexes. So you can see that like if you have a list of 1, 2, or if you have a list of, even better, A and B, then it's actually an object underneath where the index 0 goes to A and the index 1 goes to B. It's kind of an implementation detail. The important thing is that it has a single number type. So 3 is the same as 3.0. There's a single number type. You don't have to convert between integers and floating points. Everything's sort of represented under the hood as a floating point number. Another detail is that there's no constants. Everything is sort of mutable. Everything is dynamically typed. So if you set a variable to say hello, A is hello, and then you can reset it to 10, and then now it's 10. And then the most important, the only sort of grouping construct in Ink is a function. So you can say, for example, I define a double to be a function that takes a number and then returns 2 times that number. And then I can do double A, and since A was 10, double A is 20. I can define a square as a number times itself, and then I can do a square of 2, or I can do a square of a double of 2, which would be 16. So you can call functions, you can define functions this way, you can define any sort of variable this way, including the function, which is what I use here. The function notation in Ink is a lot like JavaScript, where you can say like, I don't know, add, and then the add function is defined as you take 2 numbers, for example, and then you put whatever operation you want to do there. So in this case, add takes 2 variables. Your video is covering up the bottom of the terminal. Not sure what that means. Oh, I see. That is a good point. Let me move that to somewhere that's more. There we go. Thanks for pointing that out. Okay, so I think the part that everyone missed was you can define functions the way that sort of JavaScript arrow function notation works. So let's say you want to define a function add. You take 2 variables a, b, or maybe you take a, b, c. Maybe it adds 3 numbers, and then you do a plus b plus c. And then now I've just defined a function. Ignore this bit. We're going to get into that a little bit later. We're going to define a function that takes 3 variables and then adds them together and just returns that. You can so maybe you can add 1, 2, 3, and that's going to be 6. So that's sort of the basic constructs of Ink. When I designed it to be basically as simple as possible, so that there isn't really any looping construct. Instead, Ink uses what's called tail recursion or tail recursion optimization, or proper tail calls there's a lot of different names for it, but basically you use recursive functions to do what loops would do in a more sort of traditional imperative programming language like Python or Ruby or C. That's something that's more common in functional programming languages, if you're familiar with it. Ink is definitely more functional in terms of sort of the patterns that I use programming it, but mostly I don't have loops because I didn't want to have too many things when I was first writing it, and it seems to work pretty well considering I've written a bunch of stuff in it, and I don't miss while loops and for loops all that much. What it does have is it does have something of the equivalent of if-else or switch cases. So let's say you want to write a function that tells you whether a number is even or odd. So you can say is even. That takes a number, and then you can say for if n divided by, or n modulus 2, if it's 0, return it's even, and then if the mod is 1, it's going to be odd. And then you can ask, it's 2 even, and it's even, and then you can ask, it's 10 even, it's even, you can ask, is this big number even, and it's odd. So this notation is basically what I'd use for if-else's or switch cases or any sort of branching construct, where you have this value here, and it's in front of this like colon thing, and then try to match this, and then try to look at the values and find the first one that matches, and then sort of go with whatever follows that. So in this case, for example, if it's this number mod 2 is going to be 1 because it's an odd number, and then it doesn't match 0, so it skips this case, it matches 1, so then it follows this case, it returns this odd number. So that's just a funky sort of notation that I thought, honestly, I thought was cool, so I just added to be sort of the if-else or the switch case. And that's kind of the entire language. If you actually look at, you can go look at samples that I've written in the language, and it's basically all that I've showed you is what you need to be able to like read this code and understand what's going on. I have like a mandelplot set render and things like that. And so you can write, oh, and there's like a standard library where you can do, you can write simple HTTP servers and things like that. And I've written useful things in it. My notes application is written in Ink. So it's capable of being built up to useful things, but the basic building blocks of the language are pretty simple because I wanted to focus on writing the interpreter when I first wrote the language. So speaking of the interpreter, let's look at kind of how an interpreter works. So the most conceptually, what an interpreter needs to do is all of the input, all the stuff that I just typed into this sort of program, that is the Ink program that I ran, this is the interpreter program, is I'm just giving it strings of text, and then the Ink program takes that string, somehow understands what I mean by it, and then returns the result of evaluating it. So if I give it like 3 plus 4, it has to take the string that is 3 plus 4, and then break it down properly into the number 3, the addition symbol, and then the number 4, and then understand what it means, and then evaluate it. And the way that interpreters and compilers of all shapes and sizes work at a fundamental level is it takes some kind of a string representation of your program, and then it makes a bunch of really small transformations to it to make it into a format that you can execute on a computer. In the case of an interpreter, you take the string and you make a bunch of transformations to it, and at the end you have some kind of a data structure that you can run through like an evaluator. That data structure is usually a syntax tree or a bytecode, which is basically a sequence of instructions. In the case of a compiler, you do a few more translations, and the end sort of thing that you end up with at the end of those steps of transformations is basically a list of machine instructions, and you smush that together into an assembly file as you assemble it, and then you turn that into a binary using what's called a linker. And that the compilers are a whole separate situation, which is a lot more complicated and interesting. But an interpreter basically takes a string of expressions and then tries to parse it into a data structure that the evaluator can understand, and then there's an evaluator that goes through and tries to understand how it works. So that's a little bit confusing, but let's see how that actually works in practice. So Ink actually has a debug mode, which I forgot how it works, so let me look this up. So there we go, that's what I'm looking for. So Ink has sort of two intermediate steps before before it actually runs the program. So how inc works. So the first step is obviously just the string of the program. That's just the program text. That's like what I type into the computer. The second step is a token stream. That's basically, you can think of that as like a list of symbols. So in this case, it would be the list of symbol 3, the symbol plus, and the symbol 4. In a more complicated example, like a function declaration, it's like the symbol add, the defined symbol, parentheses, a, comma, b, comma, c. These are all like individually separate symbols. And Inc turns that into just a flat list of symbols. Are we doing okay on streaming? Let me just check. Cool. And then the third step is a syntax tree. And the syntax trees can be really complicated. I tried to keep it pretty simple. So the syntax tree is basically a tree data structure where you can kind of see the nesting relationships between symbols in the program. So for example, if you have, just as a small example, if you have 3 defined as, or a, you can't define a number, 3 defined as like 1 plus 2 divided by 4. Then there's a bit of a hierarchy to this syntax, right? So like 1 plus 2 is its own thing, and then 1 plus 2 is like one thing, 4 is another thing, and the divide sort of connects it. So you can see this as a tree where like a is a thing, or there's like at the top level there's a single binary expression that is this, and then on the left side there's the simple a, on the right side of that expression there's this thing, and then under this expression this is sort of another binary expression of like dividing two things. On the left side there's this expression, on the right side there's, so it's a bunch of nested trees. And once you have a list of tokens that like that's just a flat list of like a and then defined symbol and the parentheses and then so on, you can coalesce that into sort of a tree format. And that's a little bit more meaningful, right? That's a little bit closer to like the actual semantics of what the program's doing. And so every transformation in an interpreter, you're trying to do some easy transformations to get a little closer to the true sort of what you want to end up with, which is usually a little more meaningful than the last step. So you have a syntax tree, and in the end, there's sort of the evaluator. Evaluator. There we go. And the evaluator is really just a program that walks the tree, that like looks at a tree, looks at all the symbols, and then kind of runs itself to try to run what the tree encodes. So evaluator is its own program. So the interpreter in the case of Inc is written in Go, and so there are Go programs that do each of these steps, and you just gotta smush them together, and you have the interpreter. And so when I was writing the Inc interpreter, this was the very first sort of interpreter of any kind that I wrote of this level of complexity, and so I added a bunch of debug information and debug steps to it. So we can actually look at these intermediate representations. So let's start Inc this time, but with a debug Elixir. So Elixir, or a tokenizer, is sometimes what you call the token stream. So in between steps 1 and 2, you have the Elixir, or tokenizer. And in this case, we're going to make Inc output the token stream that it encounters. So if I put in, for example, 1 plus 2, there's actually 4 tokens, 3 or 4, just a little bit fuzzy. There's 3 tokens that Inc found here. Inc automatically adds a comma at the end of every line, just so you can put expressions next to each other on a single line and it still works. It's kind of an implementation detail, but really there's 3 tokens that we gave Inc. There's the number literal 1, which is like stands for the literal floating point number 1. And then there's the addition symbol, and there's the symbol 2. This is kind of an interesting. What if you do like I define a function that's square, it takes n, and then it multiplies n by itself. Okay, so this is a little more interesting. So Inc recognized that SQ is a single symbol. It's a single identifier for a variable SQ. It's not S and Q, it's just a single SQ symbol. And then there's a define symbol. There's an identifier n, the function definition, the arrow function arrow here, and then an identifier, a multiply sign, and another identifier. And this works even if I smush it all together. Like n times n. It still found all the symbols. So the challenge of writing a tokenizer or Elixir is it has to be able to just get a series of characters and figure out which ones belong together. Different compilers will do this a little bit differently. Some steps will, this step in some compilers will do more than this step in other compilers. Ink's tokenizer tends to try to get as much meaning out of what it's seeing as possible. Other languages, especially ones that allow for macros like Rust's, will try to break it down even more. So, for example, the greater than sign, this is going to be an error because this is doing nothing. But if I do equals and the greater sign, this is two symbols. But if I do this, this is a single symbol. So these are two different symbols, and the interpreter sort of recognizes that. And so this step of the tokenizer takes a bunch of strings, and then it turns it into a list of symbols. The next step, we're doing on time. Great, we're doing great on time. The next step is a parser. And more complicated interpreters and compilers will have multiple parsers that do different kinds of transformations. Ink just has one because it's really simple, and the language itself is designed to be. What the parser does is it basically takes that token stream, that list of symbols, that's just a flat list in a single order, and then it tries to turn it into a syntax tree, which is a little bit more meaningful and shows the sort of nesting relationships in the program. So to see what that means, we can debug parser instead. This time, if we type 1 plus 2, it tells you, okay, the parser said this is a binary expression. It's the binary expression of the number 1 added to the number 2. Okay, that's kind of simple. That's not really surprising. What's a little more interesting is if we do like 1 plus 2 divided by 4. So in this case, so it's a binary expression between this thing and then division and then this thing. So this is the number 4. We know what that is. On the left side of this expression is a whole other, specifically, it's an expression list, which is sort of what the interpreter calls a parenthesized expression like this. It's an expression list, and this list of expressions only has one expression in it. It's the binary addition, it's the binary expression of a number 1 added to a number 2. So you start to see sort of this nesting relationship build up. A more complicated one is a function definition where you say square is n times n. Okay, so this is, there's more going on here. So this is a binary expression. That's a definition. So in Ink, a definition of like, let's take this function and set it to this variable. That's another binary expression because there's something on both sides. So it's a binary expression. On the left side of that expression is just the identifier sq. That's what the variable name is. On the right side is a function definition, specific definition with the argument of identifier n, and then a binary expression of the identifier n multiplied by the identifier n. So it recognizes the sort of semantic structure of what I'm typing, and the parser is constructing that tree. In Ink does it basically turns the token stream into a complete sort of deterministic tree so that we can look at the tree and figure in which order we need to evaluate all of the expressions. So the point of a parser in this case is to return sort of a tree structure where we can look at it and say, hey, we can just evaluate everything from the bottom up, from like the smallest bits up, and we can just do that until we're at the top of the tree, and then we'll have the result of the program. So that is the parser. Another interesting thing to look at is sort of the if-else expression that we looked at earlier. So we can say is even. We can write that is even function again, where it takes a number, and it takes n mod 2, and then if it's 0, it's even. If it's 1, it's odd. And then is even of 3, for example, would be odd. So if you look at how this was parsed, this is a more complicated sort of expression, so there's even more complexity. But this is a binary expression of the variable is even being set to this whole function definition. It's a function definition that takes a single variable name as the argument, and then a match. It says match on. So match on is sort of Ink's word for this if else thing. It's what's called the match expression, and it's just the name I gave it. The match expression matches on the expression list n mod 2, and then it matches it to a bunch of clauses, which is what I call these little prepositions. So the first clause is the number 0 going to the string even. The second clause is the number 1 going to string odd. So now there's a lot more structure. Now it's not just 0 and then arrow and then a quote and then even and then a quote and a comma. We have the full structure of the program sort of parsed out, and that's what the parser does. And that's another little bit of Go function that sort of runs in the interpreter. Okay, so now once we have this structure, and then there's another one which is a function call. So in this one, this is just parsed as a function call from the of the identifier is even, which is a variable, and it takes a single argument, which is the number 3. So now that we have this tree, we can kind of see how we can start to evaluate what we typed in, right? So if we, for example, if we type in this thing, let's just turn both debuggers on. So so if we type in 1 + 2, for example, we'll have a bunch of tokens that the interpreter sees, and then the parser will parse that into a tree of, we have the number 1, we are adding it to the number 2. And once we have this expression, as long as we know how to as long as the interpreter knows how to perform addition, we can evaluate this expression, right? Because we know that this is addition, we know what the left side is, we know what the right side is. If we have something more complicated, like 1 + 2 + 3. Okay, now there's a bunch more tokens, including parentheses and things like that, but we end up with a binary expression that's 1 + 2 + 3, and so we can sort of evaluate things bottom up, and then that'll get us the result to the expression, which is 6. So in other words, we can look at the sort of what's at the bottom of the tree, sort of the lowest level of the parse tree, which is the binary expression adding number 1 to number 2. Okay, so we know how to do addition, so we know that's number 3, and then we can evaluate like the next level up, which is the number 3 that we just got, plus the number 3, and that's 6. So we can imagine writing a program that takes the result of this parse step and just runs the program based on it. And that is exactly what sort of the evaluator does. And so the evaluator just looks at the tree, it knows how to perform the actions that are required of every type of expression in a parse tree, and then it just performs it. More complicated interpreters will have another step here where it generates bytecode that tries to give it a little more performance, but Ink is basically as simple as you can make it, where it just walks the syntax tree and then tries to perform the actions that are required of it. And so if you look at the Ink source code, I think that is probably the wrong file that I'm looking at. If you look at the Ink source code, there's basically a different Go program file for each of these steps. There's Elixir, there's a parser, there's an evaluator. In the evaluator, you can see, for example, there's a function that corresponds to evaluating all different types of expressions. So for example, this giant thing is an evaluator for binary expression nodes. There's another, this is a very long function. There's another one for evaluating expression lists. There's another function for evaluating like number literals and string literals. And so the interpreter knows how to evaluate each of these different types of things that appear in the syntax tree, nodes that appear in the syntax tree, and it just goes bottom up through the syntax tree, bottom up through this nested structure, from the innermost structure to the outermost structure, and runs these eval functions to just evaluate the resulting values until it gets to the top and until there's a single value remaining. Does that make sense? If that doesn't make sense, feel free to throw questions in the chat. Wow. So that's the basic structure of the interpreter. If you are curious how the source code for Ink works, it's open source, you can go look at it. I can walk you through it briefly for the curious. This is the Elixir. The Elixir, again, takes a bunch of strings, and it tries to split it up into meaningful tokens. So there's all of these constants, sort of these names that I give to the various different tokens. There's not too many. So you can see there's different names for it, like a subtract operation is minus, there's like a negation operator, there's an add operator, multiply operator. So these are all the different tokens that can possibly exist. And then we have our this is our sort of token object or token struct. This is our token object that basically represents each token. We have what kind of token is it, and then if it's like a variable name, we need to store the name of the token. Or if it's a number, we need to store the value of the number, and so we store that here for the token. And then one interesting thing that you have to do when you're parsing these program files is you need to remember where in that file, in the program file, where in the text file that token appeared. The reason is that when you inevitably have like a program error, and the program breaks and it has an error, you want the error to be able to say, hey, I broke here, and I broke for this. Find me in, like this particular file in this particular line in this particular column, so you can go fix it. If you have like a 1,000-line program and it just says, hey, I broke because of this reason, you can't find it. And so each token keeps track of its own position in the file that's running, and then this position is passed all the way through this entire pipeline to the evaluator, and when the evaluator sees an error, it looks at the position property of the token that caused the bug, and it spits it out so I can go fix it. So that's Elixir. And the actual tokenize function that you see here, this thing, just basically takes a string. It actually takes a channel of, I think a channel of characters, which was a bad choice. But it takes, actually it takes an IREAD. Basically it takes a string, and then it has a giant, where is it? It has a giant switch case where for every character it sort of switches on what kind of character it is. So you can see, for example, like for all these possible characters that appear, if it's like this symbol, the token that corresponds to is a negation. If it's this symbol, the token that can only correspond to is an add operation. There's more complicated cases, like if it's a dot, we have to see, is it a dot that's inside like a decimal number, or is it a dot that's supposed to be like accessing a property of an object? This is another complicated case where like it can be like a part of a colon character for like a matching expression, or it can be a single colon that's used in like an object literal. So it just walks through the string and figures out which tokens are. The parser basically takes a list of tokens and then it constructs the tree. This one is a little more self-explanatory. There's a lot of literature existing already out there on writing parsers. There's also programs that'll generate a parser for you, like write the parser for you if you tell it what kind of grammar your programming language has. But Ink has what's called a recursive descent parser, where it basically says, hey, let's parse this program. Let's look at the first value and see kind of, it basically has a bunch of functions that correspond to being able to parse each kind of expression, and then it calls each other recursively, so it's kind of a mutual recursion-based structure. It's a little bit more complicated to explain, but you may be able to read through it on your own and figure out what's going on there. The more interesting part, I think, is the evaluator, where you basically define these little small functions that are able to evaluate little small chunks of the program, like evaluate an object literal, or evaluate sort of a list literal, or evaluate a function definition. And then you can recursively call these things to then be able to evaluate the entire program, as I showed earlier. So that's really the interpreter. And then when I type ink here, it's just running that in a loop. And when I give it a file to run, it's just taking the entire contents of the file, running it through that entire chain of things, and then in the end, it has a value that it results, and then it just prints out the value. And that's kind of all there is to it, really. So that's a pretty simple, that's about the simplest interpreter that you will probably ever find. There are a lot more that you can do with an interpreter to make it better, make it faster. And some of those things I want to talk about a little bit. So this is sort of, I guess, the part 3 of the stream. It's like, what can I fix about Ink if I wanted to work on it more, which I don't really, it works fine. But one of the things that, so here's sort of a list of things that interpreters can do that are in sort of a non-specific order. So one thing that Inc does do that not all interpreters do, is what's called proper tail calls or Telecoil Optimization. So if you have, so let's take like a recursive function. So let's take like Factorial, which takes a number, and if the number is 0, or if the number is 1, it returns 0. Otherwise, it returns n times factorial of n minus 1. I think. And then factorial of 10, for example, is, that didn't work. Live coding is a whole thing. Why wouldn't that work? Interesting. Shall I try that again? Takes a number. If the number is 1, return 0. Otherwise, I feel like this is right. Or maybe I just forgot how to write programs. If this doesn't work, I'm going to just give up. Hey, whatever. That's okay. I guess I forgot how to write factorials. That's fine. The Telecoil Optimization, there's a great Wikipedia entry on it. You can go read about it there. But basically, when you do recursion, when you get rid of while loops and for loops in a programming language and use recursion instead, you might want, for example, like an infinite loop that can recurse infinitely. So you might be able to want to be able to call a function inside itself multiple times, infinite number of times. And in a normal, if you just have the interpreter that's basic and just the way that I described it just now, anytime you call a function inside of another function, it's going to allocate a bunch more memory because it's calling into another function. You know what? I want to figure out. Should I figure out what I did? Should I figure out what I did? Never mind. So if you have like a factorial, for example, and you do a factorial of a very large number, it's going to call itself recursively into itself multiple times, and at some point it might run out of memory because it doesn't have enough resources, because it just keeps allocating memory until a function's done running. So a Telecoil Optimization basically takes recursive functions and internally in the interpreter transforms it into a flat while loop or flat for loop. And the live stream died for me. And some interpreters, like Inc's interpreter, is capable of sort of doing that transformation internally so that you can run infinite loops and you can run very large loops in while writing recursive functions. Another thing that some interpreters do is, so in Inc's implementation, the evaluator basically just takes the syntax tree and just walks it and runs expressions that it encounters in the syntax tree directly. This is simple, but it's also pretty slow because you have to go up and down this really complicated structure. You have to basically evaluate things in a very nonlinear order because you're going up and down a tree. Whereas what some interpreters will do is they'll have this intermediate step of like a bytecode generator or a compiler. What this does is it takes a syntax tree and it tries to sort of compile it down to a sequence of lower level instructions. So for example, if you have 1 plus 2, instead of saying 1 plus 2, it'll try to convert that into an instruction with some arguments. So it'll say add 1, 2. If it's 1 plus 2 plus 3, maybe it'll say add 1, 1, 2, and then it'll have another instruction that's add to the previous result 3, just as as a really simple fake example. Basically, it takes expressions that are sort of this complicated tree structure, and it tries to compile it down to a flat linear list of instructions. And what this does is, and this is called bytecode. It's sort of like fake machine code instructions, if you want to think about it that way, or like fake assembly, to grossly simplify things. And then the evaluator can be a lot simpler, and it can be a lot faster because it's just going through a quick loop of all the instructions that it's seeing, and the evaluator only has to be able to understand these simple instructions and how to evaluate them. And most of the complexity of like going up and down the tree and looking through conditionals and things like that and calling functions can be sort of put inside this sort of 3.5 step of the bytecode generator. A lot of production sort of languages that we use have this step just because it makes the programming language a lot faster without adding a lot more extra machinery. I didn't because I just wanted to finish the project, but Lua, for example, has a bytecode generator. I've actually written about it before, as I've talked about at the start of the stream. Python has bytecode. Ruby also, I believe, has a bytecode generator. Most languages employ this little trick to make the interpreter faster and to be able to like add another layer of abstraction in the interpreter where you can mess with the stuff here without having to like mess with the evaluator, which is a lot more sort of performance sensitive, so you can slow it down a lot more accidentally. So bytecode is another thing I could potentially add that would make the interpreter a lot more interesting. The last two things I'll talk about are exceptions and memory allocation. So Inc is written in Go, and anytime I create a value in Inc, that is to say, like anytime I like type in a number, so like if I type in like 34, Inc has allocated memory somewhere that says, hey, this is like the value 34, hold on to this value. Or if I do like x is the string hello, it's allocated like some memory to store the string hello, and it's saying, hey, value x, like hold on to this value. And if I do like x plus world, and it's allocated the string hello world in addition to the other string hello. So it's always just kind of creating these values in different places in the program to be able to run Inc programs. And that's most of the time unnecessarily heavy on memory usage, because we're never going to use this. If we reset x to like 3, for example, or 2, we're never going to use this hello value again now because nothing's referencing it. The only thing that was referencing it was x, and I reset it to a different value. So it would be really nice for our memory usage to be a little more efficient if we could recognize when values were sort of out of scope and we could get rid of them. Like, we don't need this hello anymore, so we can take the spot that's storing the spot in the memory that's storing this value and get rid of it, and use it to store something else, so we can reuse our space a little more efficiently. Inc currently is incapable of doing that because it doesn't have any concept internally of like how many variables are pointing to certain things and when can we stop using places in our memory. But a lot of other languages are capable of sort of making those inferences and collecting them. So Inc, for example, instead of making its own decisions about when to get rid of values in memory, it depends on Go's garbage collector because Inc is written in Go. But you can, for example, imagine a situation where like you have a function, and after that function is done calling, it gets rid of all of the memory that's allocated inside. So it can be a little smarter, and a lot of interpreters are a little smarter about when memories are allocated and then when it can be freed. Inc just happens to offload that sort of responsibility to Go because I didn't want to have to write a memory allocator. But memory allocation is a really interesting area that you can. It's one of those areas in programming languages research where you can really spend a lot of time, and it's a really rich area. The last thing I'll do is actually a mistake that I made when I was writing the Inc interpreter, which is that I don't keep track of the program stack. So by the program stack, I mean like, okay, if I have function A, that's like, if I have a square, that's n times n, and if I had double, that's n 2 times n, and I want to double the square of 3. That's 18. When I call this function, the first thing it does is it tries to call double. And it realizes to call double, I need to figure out what this is. And so it calls square inside of the call to the function call of double. So there's sort of a stack of functions that are forming in memory. And let's say you're running square of 3, and an error happens, or like the program crashes. Normally, when let's say in Python, for example, when you do that, it prints out a stack trace. If it says, hey, there's an error happened, it happened while calling the function square, which happened while calling the function double. And that the Python interpreter is capable of printing out the entire stack trace because it keeps track of, it manually keeps track of all the functions. To be able to do that kind of an error trace, the interpreter has to know, every time it calls a function, it has to record, okay, now we're inside the double function, inside the square function. Inc doesn't do that because I didn't know that it had to do that when I was writing it, and so it doesn't do that. But if I were to do it again, every time the function gets called in the evaluator, which is the thing that calls these functions, I would probably make a little record that says, hey, I'm calling this function now. This function is like defined in this part of the file. So whenever, anytime errors happen, stack traces are the most useful. This is also a general tip, I think, for if you want to write your own interpreter or your own compiler. Having really good error traces and really good debugging for the language is really, really useful for not only hacking on the language itself, not only like writing in code, but also writing the interpreter itself, because anytime something breaks, it basically gives you the ability to shorten that loop of like, okay, we need to see what broke, we need to go and figure out where the error is, what the error is, and things like that. And so keeping track of the stack and the stack information more manually is something that I wish I had done when I was writing Inc. I guess that's kind of it. That's a little bit of an underwhelming conclusion, but that's how the Inc interpreter works. Oh, did I? Okay, apparently. I just to redeem myself before I go, I'm going to try to redo the Factorial because apparently live stream nerves had me reverse the cases. It takes a number. Yes. This is the correct version. Okay, so in a factorial, if the number is 0, return 1. Otherwise, multiply it by the factorial number. So factorial of 6 is 720. There we go. Factorial of 10 is 3 million something something. And in this case, if you call factorial 1 or factorial 10, it's going to call factorial 9 under it, which is going to call factorial 8 under it. So you can see how it gets out of hand pretty quickly, and it'd be nice to optimize that in with. That's what the Telecoil optimization that I discussed earlier does. And that is how Inc works. It's actually pretty cool to be able to, if you notice, the nice thing about interpreters and programming languages and sort of building these things is that these are all really just composing little pieces together. Like, all of compilers and interpreters is just little tiny pieces that do little transformations. Like, the Elixir is a completely separate program that you can write and test separately than the parser, which is a completely separate thing than like the bytecode generator, which is a separate thing than the Evaluator. And these are all things that you can build and test separately and build pretty incrementally. And at the end, if you combine it all together, you can, run 100-line, multi-100-line programs in your own programming language. And I think the coolest part of building interpreters and compilers is that you can build these small pieces, and when you design them correctly and when you put them together, they can and do accomplish pretty complex, pretty amazing things. And that feels really cool to be able to create and be capable of creating and just understand how it works. And so with that, I think I'll close the stream out. If you have any other questions, feel free to put them in the comments. If I come back on YouTube in the next couple of days to try to answer them, or if you're in the Nlight Slack, nlight.xyz, if you're in the Nlight Slack, ping me and I'll be happy to answer any of them. Just for the people that didn't come in at the start of the stream, I have a blog where I've written about programming languages and interpreters a couple of times. In particular, I want to highlight two things. I want to highlight build your own programming language, and I want to highlight the Lua post which is the interesting things of the Lua interpreter. This is basically the written version of this live stream. So if you're interested at all in building your own programming language, which I think is by far like the most interesting project that I've ever worked on in the last few years, this is like a 2,000 word post on all the things that you will need. I don't really tell you everything because there's a lot, but I do point you to other people who know what they're talking about better, so you can read about them. Other books, other ebooks, most of them are free resources or talks. And this is a good place to start, I think, for if you're just looking for resources in this area. And then if you already kind of get the gist of it or want to get into a little more advanced sort of level of things, this is a little bit of a longer article about the Lua interpreter, which is a simple C program. It's pretty readable, but there's also a design paper about the Lua interpreter and kind of how it works and the interesting parts about it. And I read through it, and these are sort of the interesting takeaways that I had. So if you're interested in sort of the more advanced details of an architecture of an interpreter, of a bytecode interpreter like Lua, this would be an interesting post that you might want to check out. But with that, thanks for staying on, for asking the question, for correcting me about factorials. And I might do one of these in the future. We'll see. But yeah, thanks for staying on.